All right, we've got at least one question on, thank you, on the series, on the series stuff. A couple bits of news, folks. There's a new MyOpen Math that'll open this afternoon. I know you're gonna get right on it, but if you're not done by Friday, bring your laptops and we'll work on it, probably talk a little bit more, but it's some newer stuff. It's infinite sums and a very particular type. It'd probably be good for us to do a work day in here on it so we can talk. I don't know what Monday is going to hold. It'll probably be more infinite series stuff. Next Wednesday will be a skill check day, and there'll be at least 2 new skill checks you can take on the sequences and series stuff, along with all the other ones that you might want to take. Cool. So, oh Daniel, I lost everything here. I don't know, I feel like we're out of power. But I remember the question anyway. I remember the question, so let's talk about it. So Daniel's asking about one of the current MyOpen Math questions, and I know Sam, you had some questions yourself on the sequence one. So sequences. Daniel, do you remember which one that was?
What do you mean?
Like what number?
Number 18?
Okay, number 18. Wow, I had that many questions on there?
There's 22.
What else? Wow. Wow, I'm really hardcore. Man, I really am a brutal professor. I didn't realize it until now. Sorry to make you suffer. So sequences, number 18, it was something like this. We had a sub n equals, and I'm gonna change it up a little bit, and Daniel will tell me if this is, I think you had a 2n minus something, is that right,
Yeah,
Daniel?
2n minus 2.
2n minus 2, okay. And then we'll do 3n. Was there a plus in the bottom?
Yeah, plus 1.
Cool.
Or plus
We'll do something like that. Cool. I like it. So this, I'm glad you asked about this. There's some questions I put in there that I was hoping folks would ask me about. And this was definitely one of them. Sam, was this one of yours?
Along the same lines, yeah.
Cool. Awesome. Yeah. That similar with factorials and stuff in it. So let's just remember what does a factorial mean? If I have n factorial, this is important. It's important that you understand what it is, but also how to take a formula and think about it that way. So n factorial is n times n minus 1 times n minus 2, and eventually I will get down to a 3, a 2, and a 1 if n was bigger than 3 to begin with. Is this making sense, this formula on the board? Because that is the definition of factorial. And then we had some special ones where we said that 0 factorial is defined to be 1, and 1 factorial is 1. Then from there on out, everything is kind of straightforward. So for this one, it looks a little confusing. You have to break it apart in just the right way. You've probably never seen this before, so it's understandable you wouldn't know exactly what to do. Which of these 2 numbers would be larger, the top or the bottom? The bottom, right? Because in the bottom, in the top we've got 3, and we subtract 1 from it. In the bottom we've got 3, and we added something to it. So this one is the larger quantity. So what I'm going to do is start to break this down and think about it. So let's do a little scratch work here. So scratch work. I'm going to take the larger one, 3n plus 2 factorial, and I'm going to write out what that means. And this takes some abstraction skills. So we have to be careful, and we want to proceed slowly. So whatever this number is, that goes first. That's the first thing. Then the next thing is 1 less than this number. So I take 3n plus 2 minus 1, right? Like, let's write this out. If I had something factorial, it is that something times that something minus 1 times that something minus 2 all the way down, and then eventually you get to 3, 2, 1. But whatever's inside here, and I'm doing the factorial of, I'm going to start with that times 1 less than it times 2 less than it, blah, blah, blah. So that's what I'm writing here. I'm saying that this thing here is this, and I'm going to simplify in a minute, but then this is 3n plus 2 minus 2. See where I'm getting that? And then 3n plus 2 minus 3, yep. And then let's do one more, 3n plus 2 minus 4, bop, 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 down to 3, 2, 1, eventually, one day. Let me stop, take a look at that, see if you understand that. I mean, make sure you understand that, and if you don't, let's talk about it. All right, I'm going to take that as a yes. So let's simplify. This one I can't really do much with, but this one and the next couple I can. This turns into 3n what? Plus 1. What's the next one? 3n. Next one? 3n minus 1. And then what's the next one? One more. 3n minus 2, and then blah, blah, blah. We didn't really compute, but we could. What would you hypothesize the next one to be? 3n minus 3, eventually, exactly. So then down to 3, 2, 1. Daniel's that making sense? Because you did ask about this one. So you following that?
Yep.
Okay.
Do we just choose like a random spot to stop at?
No. I'm going to show you why I stopped. So I stopped it for a very particular reason. Because I see this thing on top has a 3n minus 1 in it. And since this quantity down here has a larger, this is larger than the thing in here, eventually I've got to run into this guy. And so I'm just trying to figure out when I run into him. So that was why I kept going until I got to, oh, right there. And then this whole piece right here is actually 3n minus 1 factorial. So I'm looking for that top part as part of this bottom one. So the top part, 3n plus 2 factorial, is actually 3n plus 2, 3n plus 1, 3n times 3n minus 1 factorial. And now I'm going to put it back in there. Notice I didn't do shit to the top because it's going to cancel. That's why I'm doing this. I'm looking to see what's left after I cancel this out of this. So rewriting this all. So, oh boy, that's a nice one. A sub n is 3n minus 1 factorial over this critter, 3n plus 2, 3n plus 1, 3n times 3n minus 1 factorial. I did this work so that I could see what the difference was between these two. And then they cancel, and I'm left with a 1 over the difference here. And now it's a lot easier to think about, right? Because those factorials are confusing, especially when there's multiple ones in here. Yes,
I
Pacey?
think it got a little bit lost after that part. So when you,
Which part?
where you circled that, the end portion
Yes.
of that, I think I got confused after that. Like,
Okay, did you follow up to here?
yes.
Okay, so look at what I see here. So if you followed here, I was just taking that expression and writing it out.
Yeah.
And then I got to here and I saw that eventually 3n minus 1 showed up. And then 3n minus 2, dot, 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 down to 3, 2, 1. Because I'm just going to keep taking 1 off of this. This is a whole number, and eventually I'll get down to 3, 2, 1.
Okay.
This quantity right here, this product that I'm seeing right here, that literally is 3n minus 1 factorial. That's the definition of it. Because you take 3n minus 1, this is 1 less than that. The next thing would be 1 less than that. And I would just keep going down. So whatever this quantity is here, I'm just multiplying by 1 less, times 1 less than the previous thing, and I keep on going.
So that's from the top.
It's not from the top, but it matches the top.
Okay.
And that's what I was looking to see. So you're right, it is in the top, but this thing down here has this in it, but extra stuff as well. So the thing in the bottom is 3n plus 2 times 3n plus 1 times 3n. Notice how I'm decreasing by 1 each time. The next term would be 3n minus 1 factorial. or 3n minus 1, then 3n minus 2, then 3n minus 3. But this piece right here is that top. So the bottom is this top multiplied by 3 extra things.
Okay, I see.
Do you see? And so they cancel. So once I see that, I can cancel, and I'm left with just the extra terms that are in the bottom that don't show up in that top thing.
But I mean, I guess what are you like canceling out of the bottom? Because if that's just, oh wait, never mind. Never mind.
Does that make sense?
Yeah.
You got it? Cool, awesome. So an equals this. What happens, so the top is fixed, the bottom is getting larger. What happens to a quantity where the top is fixed and the bottom gets larger and larger and larger and larger? Smaller, smaller, and approaches what? What is this approaching as n gets bigger? You're right, it is getting smaller and smaller. If I have 1 over a number that's getting larger and larger, what is it doing? Daniel.
Approaching 0?
Approaching 0, exactly. So this approaches 0 as n goes to infinity. That's how you do that one. So what I would highly recommend just taking a little bit of time, whatever flavor you have of this, thinking it through and just making sure you think through this factorial stuff, because it will matter a little bit later. That's why we just have 1, but we want to do it now. Sam, does that feel better?
Mike, okay.
Yeah.
It's something along the same lines.
Okay.
There were multiple questions on the homework that were talking about converging.
Converging and diverging?
Yes.
Yes.
What do those mean?
So that was in the lecture you probably haven't
missed.
watched
Okay.
yet. But converge
Is
means
that where just,
it settles down.
okay.
So if you look at a chart of the sequence terms, and I talk about it that day, so you make sure you
Okay,
watch
I'll
that. But,
watch it tonight.
but if you have a sequence that is, if you look at it as a sequence of dots, and they settle towards some value, so let's say that this is A1, and this is A2, and this is A3, and A4, and this is just their height represents the value. Like 1 minus a half, 3/4.
Yeah.
This thing looks like it's settling down to some value, so I would say the limit. So first off, I would say that the sequence a sub n converges because it settles down to a single value to C. And it's cool. It's cool to talk about this again. I'm sure that it's not like everybody's not a master of convergence and divergence yet. To diverge, it would be a sequence like this. -1 to the n. Let's say I have b sub n equals that. So b1 is -1. So there's 1, so b1 is -1. What's b2? What's b2 say? So n equals 2. What do you got? Yeah, -1 squared, right? Okay. You're thinking it's harder than it is. I know. It's okay. 1. And then what's the next term? 3. So what's b3? -1. And I see
It just
this.
goes back and forth.
Back and forth, never settles down on anything. That's divergent.
Okay. Oh yeah, that makes sense.
Does that make sense?
Yeah.
So, and that's one kind of divergence. Another kind would be that I just grow and never settle down.
Be exponential.
Exponential, so something like this. If I said 2 to the n, if I looked at that sequence, let's say c sub n equals that. C1 is 2, C2 is 4, C3 is 8, just blows up. That's a divergent sequence.
Okay.
And it could happen to minus infinity too. Slap a little minus in front. And we watch it just plummet. And that's pretty much the 3 ways that divergence can happen. If it does anything else, it's converging.
Okay.
Does that help?
Yeah, thank
Cool.
you.
Yeah, and what I would recommend is looking at the values, like plotting them out a little bit, and yeah, seeing what's happening.
Okay.
Yes, Quinn.
So diverging is like as n gets bigger, the values that you get are more like away from each other.
They never bunch up.
Yeah.
Yes, exactly. Yeah, exactly. Cool.
So I got another question.
Yeah.
So, say you're given a function,
Mhm.
and would an easy way to figure out if it converges or diverges is plug in a value for n and then c? Or multiple values for n?
Yeah, in fact, let's take a look at one right now.
Okay.
Let's practice one that might not be super obvious.
Okay.
And if we don't get through all of the geometric series stuff today, if you, it's all good. We're still consider Friday a day to bring your laptops, and we'll work and maybe talk about some things. But let's say I've got this sequence here, Sam. I've got a sub n equals minus 1 to the n times n plus 1, so like kind of all together on top, over n plus 2 in the bottom. Actually, I'm going to put a little plus 1 there just to make, I like to start off positive just because I like it better. Doesn't really matter. Can we take a minute together? Determine on your own, does this converge or diverge? And what I'd like you to do is plug in some, do it with your favorite method. Think about it, get some values. Anytime you have a sequence, find the first terms. Find some terms, like put in n equals 1, n equals 2. What the heck is this thing doing? Get a hold of it, no matter what. Hey, Leo. Hey, come on in. We're not locked out.
First time, right?
I know, right? Yeah, that can was still there from Monday.
Oh, really?
Yeah. I think we should leave it there.
It was still propped up.
Yes.
Really?
Everything was still on the board. It was, no one visits this room except us. So Leo, we're looking at this sequence and trying to determine if it converges or diverges. This guy right here.
Oh, that one? Okay. Sure.
And that's news for stuff.
Professor,
Yeah.
you're saying over here that A of n converges to C. What do you do with it by C?
You actually, Quinn, at that point, you would probably need to go back to some calculus 1, finding limit kind of stuff. So like L'Hopital's rule or something like that. Yeah.
I don't know if the homework accepts C as an answer.
Accepts what?
C as an answer.
Well, this C is just, I'm just saying, I don't know what that is. I just made that number up. So that C there, I mean, whatever this value represents, I just picked a label
Gotcha.
so that I could write this statement right here. Yeah, yeah. These terms looking okay? Yeah. And once you get the rhythm, it starts to become a little easier, right? You see it's switching sign. It's going plus minus, plus minus. The top is always 1 less than the bottom.
Yeah, I think the
Yeah,
signs
it's
are
positive 2/3, negative 3/4, positive 4/6.
Well, wait. Oh, you're right. Thank you. Yeah, and I even said let's start with positive. Thanks, guy. Thank you. Yep, you were so right. Thanks. Yep, good stuff. Don't let me get away with that shit. Thanks. I'm glad you saw that. So let's look at a little plot here. So when n equals 1, let's see. Here's 1. Here's minus 1. I'm picking those for good reason. So the first one is 2/3. And then the next one is minus 3/4. So it's actually further away from the axis, right? So there's minus 3/4. And then then I've got positive 4/5, that's up a little higher. And then I've got minus 6/5. And that's a little further down than this guy. That's a little too, that's not quite right. There's 3/4 minus 6/5. What do you think's happening?
It's divergent.
It's diverging, yes. Yeah, and what's the top part headed toward? What do you think? You going up, but does it cap off? Does it keep going? It does, it kind of levels out. What does it level out to? 1. Yeah, so let's look at that. Think about this sequence. Let's go back. Just look at the part without the alternation, and sometimes that can be very helpful. So without the alternation, I'm just going to look at that. And the Quinn, this might be a way to answer that question you asked as well. So if you look at this quantity, as n gets bigger and bigger, the 1 and the 2 don't matter when n is a gajillion, right? When n is super large, +1, +2 doesn't matter. So this thing is just getting closer and closer to 1. You could either use L'Hopital's rule, so if I asked you to find this, limit as this goes to infinity of this, you could use L'Hopital's rule, which says take the derivative at the top. Well, I have an infinity over infinity form. This is going back to some Calc 1. And I could take this limit, derivative at the top is 1 plus 0. Derivative at the bottom is 1 plus 0. Just get 1. So I've got this quantity here that's getting closer to 1. And then I've got this little like pacemaker attached to it that flips it back and forth. So half of it's going to 1, the other half's going to minus 1. So you've got two kind of convergences here, but since, as Daniel said, it diverges because it doesn't entirely settle down to one value. So this diverges. Yes, Sam?
Would it converge if you go negative?
No, and we have to be really careful as well because when n equals -2, that's not even defined. So I'd have to be careful. But it would do the same thing in the other direction. So if we got rid of the throughout n equals -2 because we know it's trouble, I would actually see this thing doing the same thing kind of in kind of a flip way, but it would also go.
Okay, interesting.
Yeah. Yeah, great question. Cool. Any other questions? All right. Feel better? Quinn, you feeling a little okay about the limit stuff maybe? It was kind of, though, like not a full treatment, but like one example of how to find that limit. And you'll feel okay. Actually, you seem like you're on this stuff. I can tell. You just look confident. Just like chilled back, just smoking a pipe. In a tweed jacket, just like. Okay, any other questions on the homework that you'd like to talk about? No? Cool. All right, let's, and I'm going to answer Quinn's question again in a very specific context. I want to talk about a certain kind of sequence that's going to be really important for us. So let's talk first about geometric sequences. I don't know, did I already mention this once? I feel like I might have said it, but maybe not. Yeah, it sounds like I did, but let's talk about it again. So a geometric sequence there's a common constant ratio that doesn't change between terms. So let me show you what I mean. So for example, I start off with a 3, and I multiply by -1/2. So I'm going to multiply by -1/2, and that gives me -3/2. I'm going to keep things in fractions because it'll just be easier. We're multiplying fractions when we keep fractions. Multiply by -1/2 again. The next term, now notice I'm using commas here, is +3/4. And then the next term here is what? What's the next term?
-3/6.
multiply
3/8.
3/8, negative 3/8, and then so the bottom just keeps going up by a factor of 2. You see that? The top is staying the same, and the sign is alternating because of this minus. So the next term is 3/16, then minus 3/32, and we just keep on going that way. That is called a geometric sequence because to get from term to term, I just multiply by the same number. So here the common ratio is r equals negative 1/2. So this r is a common notation for that ratio. I mean, ratio starts with r, right? So it kind of works. Let's do another one. I've got 2, negative 8, 32, negative 128. Is there a common ratio? Are you shaking your head, Leo? Yeah, I can't tell. I couldn't tell if you're shaking your head or your whole body. Yeah, yeah. What's the common ratio? Negative 4. Yes, negative 4. So times negative 4, times negative 4, times negative 4. Now, I kind of want to ask you a question since we just talked about this. Do you think this sequence is doing anything, settling down? Let's plot a few more out. So we're going to, actually, what is it, when you take a half of a half of a half of something, what happens to it? Shrinks, right? It shrink, or you keep having something that shrinks. So I've got this quantity that I'm taking half of. So it's shrinking in magnitude. The sign is alternating, but if I were to plot these points out, what I would see is something like this. So here's 3, that's my first term. And then the next one's below, but half, 2 times closer. It's half the distance. So when we go here, then we go here, 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 here. So sometimes getting that graphical representation really makes all the difference. It looks like it's converging to what? 0. Yeah, it's converging to 0. Does this look like it's converging, this second one? Not at all. So this one converges to 0. This one is divergent, or it just diverges. You can say it diverges, it is divergent. Both these things are totally acceptable ways to say that. So notice here, the common ratio here, I was taking a fraction of what I had before. Down here, I'm expanding what I had before, at least in terms of magnitude. I'm blowing it up. So we can kind of make a general statement about this. So in general, let's make a nice little rule that you can have on a note sheet next to your side. A times r to the n, so that's a times right there, is a geometric sequence. And they can all be made to look like this. And we, in general, that if r, the magnitude of r, so that's absolute value, is less than 1. So that's like everything from just a hair above -1 to just below +1. The series converges, or the sequence, a times r to the n converges to 0. So it converges. And it converges to 0. It dies out. You're taking a fraction of a fraction of a fraction, whether that's a positive or a negative. If it's negative, it oscillates to 0. If it's positive, it just shrinks to 0. If r equals 1, what happens? If r is just 1, what does that sequence look like? Same, it's just a, right? So if r is 1, 1 to the n is 1, It's just constantly A. So it's a constant sequence, and that's convergent. That's the greatest convergence of all. Things are just always the same. So we've got R to the n. So if R equals 1, it converges to A. It's constant. It's a constant sequence. That's super boring. We're never going to have that. But we got it. Any other R value, it diverges. It diverges everywhere else. So, all you have to do is identify, is this geometric? What is the R? And you know everything about it. If the magnitude of R is bigger than 1 or R equals -1, if R equals -1, it's just going never settling down, it diverges. So let me ask you this. Is that a geometric sequence? It is not. Why not, Sam? I agree.
Because you're just taking previous, so to get 3, you take the sum of the previous 2.
Yeah, because this is we kind of need, yeah, exactly. So this is like that Fibonacci sequence, right?
1 and 2 to get 3, 2 and 3 to get 5, 3 and 5 to get 8. So
Exactly. So is it geometric? No.
So in this case, would R be the formula of like the previous value plus?
No, so for R, so Quinn, let's focus on this. That's good. So this one, we're like going, oh, that's Fibonacci. And it still could be geometric. Let's check. What do you multiply by to get from here to here? This is what the R is going to be. 2. So that took times 2. What do you multiply by to get from here to here? 1.5. It's instantly not geometric because a different number was required. So 1 point times 1.5. This is not geometric. And I can tell that immediately. I don't have to keep testing. Does everybody see that? So at this point, I just go, oh, it's not geometric. Hopefully the problem says, is it geometric or not? And if not, don't do anything. But what do you think this sequence is doing? Do you think it's converging or diverging anyway? Diverging. It's one of those ones. It just looks like it's blowing up, right? So this would be divergent anyway. But we can tell divergent. It's going to infinity. It's just blowing up. Cool. This fact right here is really important. It kind of goes up here too. So just keep in mind. And a lot of times this A will be 1 and you won't even see it there. It's just R to the n. So let's start adding these things up and see what happens. There is this ancient Greek paradox called Zeno's paradox. You ever heard of this? Z-E-N-O? No. If you were in one of my calc classes at some point, we probably talked about it and you saw me do this little show. So let's say I want to walk from this end of the board to the other end of the board. Just right down there, that first little piece of wood. Zeno hypothesized, well, wait, to get from there to there, I first have to travel half the distance. So right now I'm at the 1/2 mark right here. Then to get from there to there, I still have to travel half that distance, right? At some point, I have to cross the halfway mark. So I've just moved, so let's see, I moved 1/2 plus 1/4. Now I have to cross the 1/8 mark. And then I have to cross the 16th mark and the 1/32nd mark. And Zeno said, well, wait, I'll never actually get there because there's always half the distance still left to travel. Now there's problems with this, lots of problems. Zeno was kind of, in this scenario, Zeno's walker is decelerating. So they're actually traveling slower like slower and slower and slower and slower, and never really ever getting there. But what we're going to see is that Zeno's paradox actually has an answer, and that is that if I take these numbers, if I take the distances I traveled, so let's see, what did I do? I went a half, plus a quarter, and then an eighth, plus a 16th, plus a 1/32. We are going to see that that adds up to 1. So this is our first example of an infinite sum. So this is an infinite sum, but we've got a better word for it. It's called a series, an infinite series. So just remember this, series means you're adding. That's a sum. Sequence is a list. And people get this messed up all the time. You will definitely mix these two terms up at some point when you're just starting to learn about them. So that's our first infinite series. And we're going to prove today that Zeno made it across the board. But we got to start a little slower. So let's think about first finite geometric series. So this means there's a finite number of terms. It ends, the sum ends. So here we go. First, I'm going to define this thing called S sub n. And this is going to stand for the nth partial sum. In other words, it's the sum of the first n terms. And the terms are the things I'm adding. So whenever I have a sum, these are the terms. So this sum is going to look like this. I'm going to start off with some number a, and I'm going to multiply it by r and add it on. So I'm going to take a times r and get ar and add those. Let me stop. Let me see how you're feeling about this. Not done. I'm just taking a break so you can finish right and catching up. I'm going to multiply this by r. What's the next term? If I multiply this by r and add it on, ar squared. What's the next one? There we go. Got a better buy-in on that one. ar cubed, and we're going to go all the way out to ar, and I'm going to put an n minus 1 right here. And I'm doing that because I wanted n things in this list. So think about how I did that. I wanted n things to be added together. If I had stopped right here at a plus a times r, the exponent on the r is 1, but I have 2 terms. If I had stopped right here and said, how many terms are there? There's 3. 1, 2, 3. Notice that the last exponent is 2. So when there's 4 terms, the last exponent is 3. So when there's n terms, the last exponent is actually n minus 1. I'm just taking that and generalizing, thinking through that rhythm. I want to come up with a formula. We're going to make a formula to add that up, so you don't have to go in your calculator. Oh my God, he really wants me to add 1,000 terms. He really is a bastard, that Dr. T. What's next with this chump? We're going to come up with a formula, but I want to derive it for you because it's really beautiful. So multiply both sides by that common ratio r. This is a really cool thing. So I'm going to multiply this left side by r, and I get r times s sub n. Just writing it down, right? I multiply by r. Equals, now the right side, let's watch this and be careful. What's the first, when I multiply this right side by r, what's the first thing that shows up? Multiply right side by r. What's the first thing?
AR.
AR. That times R. Notice there's already an AR. I'm going to line these up. When I multiply this one by R, so here, I'm kind of like going like this, right? Times R. What's, Leo's on this. Leo, what's the next one?
AR squared.
Thank you, sir. I multiply this by R, I get AR squared, so I multiply that by R, times R. Keep on going. Keep on going. Blah, blah, blah. AR cubed, blah, blah, blah. And then eventually, the one right before this is actually, there's like a plus AR n minus 2 right before this guy. When I multiply it by R, I get AR n minus 1. And Leo, what's my last term in this series?
AR to the n.
AR to the n, take that last term times R. It just bumps the exponent up by 1. And we've got that. Cool, thank you. So I took this sum, multiplied everything by R, and I get this one. It's just this whole thing multiplied by R, and I wrote it shifted over for a very important reason, and that's that I'm going to subtract. I'm going to subtract each side from the other. So the left side, so now subtract, and I get S sub n minus R S sub n equals, what cancels over here? Well, let's see, this and this, this and this, and that's why I lined them up. And even this will cancel. And I'm left with A, which has nobody underneath them, minus, and there's like a 0 here, so I got 0 minus that term, which doesn't show up on top. Oh boy, this is cool. Now there's no more sums. There's no more long sums. The thing I'm trying to find is this. This is what I really want a nice formula for, that sum of the n terms. So look what I got here. I can factor this left side, so factor out S sub n on this side, and you're going to get 1 minus R times S sub n. And on the left side, I've got, or excuse me, the right side, I could factor an A out, and I've got 1 minus R to the n. So here, factor out A. And we're done. We're just about done. I'm going to divide both sides by 1 minus R. What's it really important that R is not equal to? 1. Yeah, because if it's 1, I got a 0 here. And this whole thing was kind of weird. So if R is not equal to 1, and if R equals 1, this is some boring shit anyway. Because if R is 1, I got A plus A plus A plus A. We don't need a formula to do that. So if R is not equal to 1, divide both sides by 1 minus R to get something I would put down on a note sheet. We're going to do some examples with it. S sub n, the sum, that sum up there, has what's called a closed form. A times 1 minus R to the n over 1 minus R. Write this down. This is the closed form of the sum that we started with. And now, let me give you a minute to get your breath and get caught up. And let's talk about how to use this formula. And I'm actually gonna write one more version of this. So, to find the sum of a finite geometric series. So finite means there's no plus dot dot dot. I see the end, both ends. I see start and I see the finish. To find the sum, this formula says the sum equals the first term. So remember this A, it's the first term. So first term times 1 minus that R raised to the nth power, finite geometric series with n terms. Add this to that. I have to know how many things are in it, how many things are in the list, divided by 1 minus r. Now we'll start an example up over here. That's the way I like to think of this with that kind of mnemonic thing. You need to know what the r is, but you should have figured out what that is because you're figuring out this is a geometric series or not. And once you know it's geometric, you know what r is. So let's do some examples. I've got, we're going to do finite, we're going to do partial Zeno. 1/4, 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus 1/128. We'll go one more, 1/256. Used to spend a lot of time with computers. You know, lots of powers of 2. Cool. So I want to find sum. And I don't want to sit around all day on my calculator wasting time. Find the sum. So step 1, note that it's geometric. And I need to say exactly what r is. And what is r here?
2.
1/2 times a half. Think of the whole term, not just that bottom part. Does that make sense? Yeah. So if it is geometric, r equals 1/2. Is everybody okay with that? Let me stop. I see nods. I'm going to make sure they're nods, I believe. Mason, I want to make sure I believe you know. Okay, that was good. I like that one. That is like, yeah. All right. Good? Good? I'm looking at everybody. I'm just like going around. Look me in the eyes. Yeah? We good over here? Okay, all right. I won't grill Quinn because Quinn just came back in.
What did I do?
N equals the number of terms. You didn't do anything. Except miss some shit. Miss a lot of shit. Number of terms. How many terms are here? 1, 2, 3, 4, 5, 6, 7, 8. There's no way Axel's going to have time to tell you what happened. What's the first term? 1/2. And that's that A from the formula over there. So the N equals, look, I got everything I need in that formula. First term, common ratio, and the number of terms. So the sum equals, let's write out the formula, first term times 1 minus, you do have to do some calculator work on this power. You have to take your common ratio to that 8th power. And then it's over 1 minus r. So this is, first term is A, 1 minus 1/2 to the 8th power over 1 minus 1/2. And all I gotta do is work that through and I've got it. Why don't you take a minute on that? 2 to the 8th is 256. And we could use a calculator. But we don't have to. We should keep things pretty. Everybody's going to use their calculator anyway. When the Russians kill our power grid, you'll wish you could do things by hand, I'll tell you that. Is this looking okay for a first move? I literally just took 1/2 to the 8th power. Boop. $255 over $256. Sophia looks pretty solid on that. I like it. Does this feel good? And if you did it on your calculator, is what you have on your calculator that number. If you multiply what you have on your calculator by 256, you should get 255 and some change. Questions on this? Sound okay? Let's do one more. One tenth minus 1/100th plus 1/100, 1,000. So actually, here, let's just do it powers of 10. 1/10 minus 100 plus 1,000 minus a 10,000 plus a whatever the hell that is, 100,000 minus plus, and we're just going to keep on going until we get to 1/10 to the 10th power, and that should be a negative, yeah. Now, that looks painful, but not if you have the formula. Use the formula. What is the sum? Sanity check. What's a common ratio? What, a 10? Is it positive a 10?
Negative.
It's negative, so keep an eye out. When you see sign changes, your R is going to be negative, so be real careful on that. If these were all pluses, Axel, I'd totally agree that it was 1/10. So here, R is negative a 10th. How many terms are there?
10.
10, yeah, look at the exponents, right? There's 10 to the first, up through 10 to the 10th. They just go up by 1 each time. So they're 10. That's right, Daniel. Now be careful about minuses and double minuses, because they're going to show up here. I envision weird algebra happening at this point, so I'm going to beg you to go slowly. This shit will never cancel. Like, if you're doing this, if you're like canceling like this, that ain't happening. Yes, did I screw something up? Because probably Emily caught it too. Yes. Yes, thank you. Good. Is that what you were asking about, Emily? Yes, awesome. Good eye. That should be 1 minus negative a 10th. You're absolutely right, which turns into a plus, Sam. Like, I'm sitting here babbling about it, and then I screwed it up.
The one on top also.
I think I'm good on that one.
You're good right there.
I'm good because I left the minus in. I haven't taken care of the 10th power yet. Where are you seeing? Or is that
the very left.
Oh,
No.
no, because that's the first term, Daniel. So that's actually just grab this. If it was negative, I would have written it there.
Gotcha.
Does that make sense?
Yeah.
Cool. This is good. These are all great questions. We're trying to understand this. So this is 1/10. I see everyone suffering over fractions. Is minus 1/10 to the 10th positive or negative? Is that a positive number? How does that differ from this?
Should be negative.
Are those different or the same? And why? Yes, I agree.
Because each factor of 2 will produce a positive output.
Yeah, nice way of thinking of even exponent, right? So because it's an even power, that happens. So that we can knock some work off that way because even exponent. And I like the way Quinn said it. You know, Quinn said every pair of negatives will cancel each other. So that's a really cool way to think of it. Are you cool on this? Yeah, okay, cool. All right, because even exponent. So then this is just 1 minus 1 over 10 to the 10th, which is a big ass number. I'm just gonna leave it like that. The bottom becomes 1 plus a 10th. And now I can simplify a little. Let's see, so we got 1 over 10 times 1 minus 1 over 10 to the 10th. And then in the bottom, I've got 11 tenths. We're almost done. I know you want to get your calculator out. I know you want a decimal. Humor me. I grew up in pre-calculator times. I remember when my grandfather got his first calculator. It cost like $500 and had like a bright red LED on it, and it did like basic arithmetic. Had like one storage unit in it. It was a Texas Instruments. It was really cool. So let's simplify a little bit. To divide by a fraction is to multiply by its reciprocal. So this is 1/10 times 1 over 1 minus 1 over 10 to the 10th times 10/11ths. So I just multiplied by the reciprocal of the denominator. I see these guys cancel, and I'm left with 1/11th times 1 minus 10 to the 10th. And this is some number. This is the sum. We could get this out. Did anybody actually get it on their calculator? I'm just curious, because this is super small.
Yeah.
Oh, we actually should be able to do that. Oh, yeah, this is actually not too bad. Let's see, it's 1/11th minus 1, and then this is 0 point. We're just going to move the decimal place over 10 times. So let's see, this would be 1/10 would be there, 1/100, so that's 10 squared, 2, so I have 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so when I do that, that's 1/11th times 0.923, 4, 5, 6, 7, 8, 9, 10, 11. Oh, and if I divide that by 11, these are all like, let's see, there's a pair. Oh shit, not perfect pairs. Can somebody do that for me? It's like 0.09, 09, and
Yeah,
then
it's very roughly just like 1/11.
it's like, it's pretty close to it, yes. I mean, yeah, that number's, yeah. Approximately, yeah. It's just a hair under. That may seem, and maybe in this one, who knows what was more work in this one. It's hard to say, at least we got some practice. Is there any questions on this at all? Because I've got a little bit, we got some time. I want to wrap this up today so we can really just practice and work on the homework on Friday. Okay, so these are finite geometric series. I want to now talk about an infinite geometric series. So for an infinite geometric series, I have some first term. I multiply it by r, and I add that on. I multiply that by r, and I add it on. So I just keep getting higher and higher powers of r, but that never ends. So now it's never going to end. So what we're going to do is sneak up on it. We're going to take a finite part of it, figure out its formula, and then let n go to infinity. So the plan is find a formula, S sub n, which is equal to the sum, and we've done all the work, of the first n terms. So in other words, it's going to look like this. Just like we started with. That's the first n terms. So find a formula for that, and hey, we actually know that formula. We did a lot of work already. So this is called the formula, I want to say this again, for the nth partial sum. It's not the full sum. It's just the first n terms of the whole kit and caboodle. And then let n go to infinity to get the full sum, the full infinite sum, if it exists. And you're going to love this, honestly, when we get done here. The formula to do an infinite sum is so easy. This is like the hard part is the finite. The easy part becomes the infinite. You'll believe me in a minute. So, i.e., we need to find the limit as n goes to infinity of the first n terms added together, which is the limit as n goes to infinity of this critter. That's our formula. I'm going to take the limit on that thing. Let me let you get caught up in writing. And what I'd like you to notice is that the limit is on n. We're letting n get bigger and bigger. N only shows up in one place, and it's the exponent on that r. So notice that this thing here is equal to a times 1 minus the limit. I'm just going to bring the limit onto the little piece that I need to understand, because it's the only piece that's moving, this thing right here, a times r to the n over 1 minus r. Just bring the limit right there. We came up with a rule for this. We know how to do this limit. This is a geometric sequence. So recall, and it's probably hard to recall because it was like half an hour ago and lots happened, that the limit as n goes to infinity of a to the r sub n equals 0 if the magnitude of r is less than 1. Remember, we did that, right? Because this thing just is a fraction of a fraction of a fraction of a fraction. And it diverges otherwise. So in other words, if the magnitude of r is bigger than 1, why would I not want r to equal 1 anyway? What would be bad if r equaled 1? What would I be doing that would like get the math police like the bottom, right? I would be dividing. R couldn't be 1 anyway. So here's all you need to check in an infinite geometric series. If you have an infinite sum, you're positive it's geometric, so common ratio. All you have to check is the common ratio less than 1 in magnitude? So between -1 and +1. If this happens, then we have a sum. Sum is finite. And if this is, so let's assume that that's true, because that's the only time this shit's going to work. Assume that the magnitude of r is less than 1, i.e., I'm going to write it again, between -1 and 1, we don't include those two endpoints. It's truly a fractional critter. Then this limit, as n goes to infinity of s sub n equals, look what happens. This goes to 0. And all I'm left with is this, a over 1 minus r. In other words, first term, whatever the first thing is in sum, over 1 minus the common ratio. That's it. So cake. After, it's infinite. Hope I didn't spit on you, Sam. I felt like some saliva came out of my mouth in your direction, so I apologize.
I feel like
You didn't feel a thing?
Nope.
No. You're hardened from the baseball diamond. So. All right. So, example. So back to Zeno. 1/2 plus a quarter plus an eighth plus a 16th plus a 32nd, blah, blah, blah. Does Zeno get across? So, R equals 1/2. You've got to check, make sure it's a geometric. 1/2, 1/2, 1/2, 1/2, 1/2. Since this is true, since R is between -1 and 1, this converges. The sum converges. In other words, settles down to one value. 2, first term, 1/2. You put that on top, whatever's in the very first thing you add, over 1 minus the common ratio. So in other words, it's 1/2 over 1/2, 1. This adds up to 1. If I have all the time that I need, which is infinite amount of time, none of us have that. This is just math shit. This doesn't exist. But it sure is beautiful. Let's do a weird Zeno. Let's do one last, I call this like Zeno's other paradox, and I just made this up. I didn't make up the series, but I think of Zeno as doing a different thing. What if Zeno did this? Trying to travel across a distance. And Zeno says, well, you know what I'm going to do instead? I'm going to go forward half the distance. But then I'm going to back up half the distance I just traveled. So I'm going to back up a quarter. And then I'm going to move forward an eighth. And I'm going to move backward a 16th. Forward a 32nd. I'm doing like a cha-cha, right? Like something like that. Like I'm not a dancer. I'm not going to try to dance in front of you. You don't want to see that. Not a great dancer. Got like this punching move I do. I'm really loose with my wife after a few drinks. But like, I basically, you ever seen Grateful Dead people at a show dancing? I do that like white person shamble, stoner shamble, whatever it is. So what we've got is 1/2 minus a quarter plus an eighth minus a 16th plus a 32nd minus a 64th. What's the common ratio? Negative 1/2. Good job. What's the first term? 1/2. Let's plug this in. So this converges. I know that it converges because R equals -1/2, and that satisfies this condition. Whoa. This condition. So the sum equals first term over 1 minus the common ratio equals 1/2 over 1 plus a half equals 1/2 over 3 halves equals 1/3. So you end up perfectly 1/3 of the way across, which is really quite odd because all these halves somehow got you 1/3. So I think that's cool. That's it for today, my friends. You should be able to do all of your questions except one on that homework. But we're going to spend Friday. Come in Friday. Let's work on it together. Thanks, everybody. That's all.